So what we shall be ended at a point where we have studied the geodesic equation, right? We have looked at, we have seen what the geodesic equation is, and today what we shall do is try to consider a family of geodesics. So there are a family of geodesics, and we shall assume that these family of geodesics, these are the geodesics, they are parameterized by a parameter tau, and see, this geodesic is different from this geodesic. So, in order to distinguish two nearby geodesics, we shall use another parameter which is h, which basically tells us that which geodesic we are considering. So, we have a family of geodesics. The geodesics are parameterized by this parameter tau, and to distinguish between each of the geodesics, the parameter that we are using is h. Okay. And so we shall start with the geodesic equation. Let me just write down the geodesic equation. The geodesic equation is I hope you can see the green board. So this is the geodesic equation. Okay, that we have already learned. And you can see that we have used partial derivatives just to because these geodesics are basically parameterized by two parameters, and its differentiation is with respect to tau, and therefore since you have another parameter here, so this partial derivative appears here, and you can write this equation in a compact notation. You can write this as tau plus gamma c. So this is the equation. You can write this in this form where you know that this is basically the tangent vector to the geodesic, right? So this is the standard stuff that we have already learned, but the only thing that we are saying is that we are now considering a family of geodesics here, parameterized by tau, and to distinguish between each of the geodesics, we are using another parameter that is h. We now define a second vector associated with these geodesics, and the vector that we define is the following. This is VA. Now we find us this XA. This is the second vector that we define. So we have already a tangent vector UA. Now we define a new vector, which is this. This is partial derivative with respect to h. Partial derivative of XA tau h. And what does it do? It tells us basically this. I'm sorry. Which one? H. H is a parameter.
Yeah, so how can you guarantee that A is a vector?
A is a vector.
VA.
VA. This is differentiation with respect to H, right? This was differentiation with respect to tau. So what is the problem?
But in that case,
I'm not saying no. We have this is a tangent vector to the geodesic. This is not a tangent vector. I'm not saying this is a tangent vector, but this is a vector. It's not a tangent vector to the geodesic. This has an interpretation. This basically tells you, this gives the difference in the coordinates of two infinitesimally closed geodesics. You have two infinitesimally closed geodesics here, and this VA gives you an estimate how much the two infinitesimally closed geodesics differ from each other. This is what it does. for a given value of tau, obviously. Because if I just, so all these lie on the same tau. Okay. So for a given fixed value of a tau, this VA tells you how close two infinitesimal closed geodesics are. This is what it tells you. Okay. So if this is clear, but this is obviously not a tangent vector. Rather, this is a tangent vector to this curve. Right? It's not a tangent vector to the geodesic. And the fact that whether it's a vector at all, you can just look at the transformation. And what about the transformation? Then it will be a vector. It will transform like a vector. So now, what we shall do is, from here, you can immediately see from these two definitions, you can immediately see that if I take a derivative with respect to tau, this will be equal to del UA derivative with respect to h. Right? Because we know that partial derivatives, ordinary derivatives commute with each other. So this immediately follows from these two definitions. So this is an important thing which we shall use immediately. You will see we shall use this. What follows. Is that part of the book? Is it? Anyway, I can just. This one? না আমি করেছি আগে কিন্তু আমি ভুলে গেছি এখন হ্যাঁ এটা শিফট করছি কোনটা দিয়ে বলো তো এটা টিপে রাখলাম তত টিপে তত ওকে দিয়ে আবার ডান দিকে করতে গেলে আবার এদিকে আচ্ছা ঠিক আছে ওইদিকে গেছে কি বোর্ডটা ঠিক আছে ওকে so now the rest is quite simple. Let me do a simple computation. The computation is not that simple. Let us do it. Let's start with computing this thing. Let us compute this quantity. So this is a covariant derivative. As you all know, this will be del VA del tau plus this is right gamma A C del XT del tau. Is this clear? Is this equation clear? Huh? It's clear. That clear as well? Because we have written this equation many times. You just go back to the definition of this thing, you will see that this is equal. But only thing is that there we have used a total derivative, dd tau was dd tau, this was also dd tau, but now we are using partial derivative. Why partial derivative? Because xa is a function of two parameters, not only tau, but it's a function of tau as well as h. So if this is fine, then let us use this one, this equation now. And from here, you can immediately write this as del A del H plus gamma A BC. This is del XP del tau, and that is UB. So the first line follows from the fact that you have an arbitrary vector tau, that is tau plus just apply this equation for VA. formula for the covariant derivative. So what we have seen, so what we see from this equation is that this particular quantity is this. And what are we trying to do? We are trying to find out. So you see that VA basically is this, the tangent vector along this direction for the same tau, right? So VA measures, as I mentioned, that it measures how close to geodesics are. And our next step, so what we aim to find an equation for this VA. What is this VA? This VA measures the deviation vector between two geodesics. It is measuring the deviation between two geodesics. So we want to find an equation for this deviation vector VA. And so this is called the geodesic. So the equation that we finally want to obtain is said to be the geodesic deviation equation. Now we shall need more space to the calculation. So next our aim is to camera shift with this one. So our next step is to calculate this. So this is also quite simple. It is basically, again we shall apply this definition, but considering this to be a vector. Let's put it there. So this will be del tau d is tau plus gamma a c d c tau. This again follows from this definition. Just replace a contravariant index small a by dva theta and apply that equation, we will get this. And rest is quite simple. We need to plug in that formula in this here and also here. So if we do that, this will give us del tau. This is del a del h plus a c. So this is this part, second line that we have substituted here, plus gamma a c d del x c del tau, and replace it by uc. Please tell me if I make any mistake here. dv d tau, so that will be del d plus gamma d used notation b here. I will follow exactly my notation, whatever I have calculated. I will not use any other notation because I will make mistakes then, and I have no time to make mistakes. So gamma dve, then this will be qb. Please check whether this is correct. Huh? Right. Right. Thank you. It's BH. So let me just check once more this equation del tau derivative del h plus gamma abc up dc gamma acd uc ud uh dp ud be. So this looks absolutely fine. So we just need to simplify this expression and nothing more. So what we shall do is simplify this here. So this part is equal to, so how many terms we will get? It's one term, two term, 3, 4, 5, 6. Okay. So what one has to do is del tau del h plus, now this del tau will act on three terms here. So you get three terms from here. So this will be del tau of gamma a b c. So this is one term. This derivative just acts on this Christoffel symbol multiplied by ub bc. So this is one term. Then we shall have plus gamma a c del ub del tau. So this now acts on ub only, bc, and then the third term it will act only on bc. It will be gamma a bc ub del bc del tau. So all the three terms are taken care of. Okay. And then we just multiply these two terms. Get two more terms, gamma a c del ut del h plus gamma a dd multiplied by gamma d de uc ud. Please check all the terms whether I have written down all the indices correctly or not. So from here, this quantity, we are calculating this quantity, the second derivative, the second covariant derivative sort of thing. So from here, you will have 1, 2, 3, 4, 5, 6 terms. Check all the indices, whether I have written them correctly or not. Let us concentrate on this term now. This term. So what we shall do is, here, we shall apply chain rule. So it will be del xd, del xd del tau. Del xd del tau is nothing but d. We have applied a chain rule for the second term. And then the next term is gamma abc del ub del tau bc, that is fine. Then we have gamma abc ub del vc del tau, that is also fine. Next term is gamma acd uc del ud del h, that is fine. Gamma acd, gamma dpe, uc ub ve. All terms are fine. Is this okay? Short term मिलेजे? So far what we have used that property, that del Va del tau is equal to del Ua del H. We have used that property by using the thing that ordinary derivatives commute, and we have used the formula for this covariant derivative. So far we have used this thing to calculate the second derivative of this deviation vector. So this Va, I am giving it a name. I am calling it the deviation vector. So we have a tangent vector, we have a deviation vector. This measures how close two geodesics are. What is the deviation between two geodesics? Now we shall use a third thing, and that is basically, so I shall just I can remove this part. Now we shall use the geodesic equation. Let us use the geodesic. And geodesic equation we shall use for the first term. That is equal to so we shall use it for del UA del tau. You have the equation, geodesic equation written in terms of UA. So del UA del tau, that is nothing but the minus of gamma A C UB BC. So in this line we have used the geodesic equation. Can you see? Is it clear? Because you just go back to your notes and see that when I wrote down the geodesic equation in terms of XA, then I wrote it in terms of UA. In terms of XA, it is a second order equation. The differentiation, there are two derivatives. It is del 2 XA, del tau 2. But in terms of UA, it is a first order derivative. Del UA del tau is basically equal to minus gamma ABC UB UC. So we have used the geodesic equation here. And the rest of the terms are all same. We have to use the geodesic. We will use the geodesic equation here also. So let us do that. Plus del B gamma A BC UB UB BC. That is the second term. In the first term, we have used the geodesic equation. Now we shall use the geodesic equation in the third term also. This is, we have another minus sign. So plus gamma A BC, the minus sign, gamma B D UV D BC. So we are using geodesic equation in this term, also this term. Del UP del tau is minus of this. So that term is taken care of. Now we have this fourth term. For the fourth term, what we shall do is we shall write this as gamma A BC UB del UC. See, we have used that equation, that commutativity relation. Once again. So what we have done is we have converted the partial derivative of BC with respect to tau in terms of partial derivative of U with respect to H. So that is taken care of. And then the fifth and sixth terms is here. That's the sixth term here, as it is. Gamma A, B, C, U, B, del U, D, del H, gamma A, C, D, gamma D, D, E, U, C, U, B, P. So I am not writing this term. This term is dot 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 stands for this one. This one stands for this one. So please write it down in your notes. Okay, good. Now we have used all the necessary things, and small things needs to be done. Okay. Next thing that we shall do is from here you can see that this partial derivative will act on this one, and it will act on these two terms. So there will be three terms, right? But you can see that you can write this as so what I mean is this acts only on this term. Okay, this is one term. And then the remaining you have two terms because they act on this and this. Huh? They do not cancel out, they add up because of this symmetry. Oh, they will have that is true. They will cancel with other term, but let me just write it down. So we will have minus 2 a c L U B H. Or you can write this same thing. In my notes, I have written this in this way. Do it in any way you like. Not deviate from my notes. On my calculation, I will just write it as del UC del H. I hope you understand why you get this term. Evanshu? Yes or no? If it is no, then please tell me that it is no. You have understood it, right? Because I am using the symmetry of this gamma Christoffel connection. It is symmetric in the lower indices BC. So if you use that symmetry, you get two terms, so the two terms will add up. So this is fine. Okay. From here, there is something very interesting that is occurring, right? That is what Shom was mentioning. You can see that this term, concentrate on this term. This was the first four terms here. The first four terms have now broken up into this one and this term. Okay? So that gave you this minus 2 term and this term. And there are the fifth and sixth terms, this one and this one, that are written over here. Now, notice that this term and this term, which is this one, they add up, right? So you can cancel this term and put a 2 here, right? And now you can see immediately that this 2 cancels with this one. So what I've done is this term and this term, which I wrote here, they have added up and gave you a 2. So I got rid of this term, put a 2 here, and this full term cancels with this term. So the terms that remains now is this one. Here you have another term, third term, and this one. Which one? The third term. Okay, that I have to see. Gamma A, B, C, gamma B, D, E, U, D, U, D, U, E, D, C, and the other term is gamma A, C, D. No, that does not cancel. Will not cancel. Okay, so what? So let us write it clearly now. Let me just write it clearly. Move this one. I hope you have written everything in your notes. Gone. It's also gone. This is gone. Let me just write this down here. This is plus gamma A, C, gamma E, D, C. Okay. So after all these manipulations, we are left with 1, 2, 3, 4 terms. We have 4 terms. And you can see what it means actually, right? Okay. So let us concentrate on this term. This term, we shall write it down as Again chain rule. Del gamma del x d del x d del h. Del x d del h. But what is del x d del h? Del x d del h is Vd. This term is taken care of. Plus you have del d gamma abc ud ubvc, that is there, minus gamma abc gamma bb ud ue bc, and then the last term gamma acd gamma db uc ubp. So we have all the terms here. Let me just put the minus sign here. It will be flat. 1, 2, 3, 4 terms. Okay, so that is good. Now what we can do is the following. You have UB and UB is there. So you can do some manipulation. Write this as what I am doing in this step is that I am trying to combine this term with this term. You have 4 terms. Ultimately, after doing all these manipulations, you have 4 terms remaining, right? And now we are trying to combine this term with this term. Okay? So if you combine it, you will find that this will lead us to the following. If you are confused, then I can work out the step. It's not that difficult. You will see gamma A B UB UC. So what I wanted to do is I wanted to take this thing common. So in order to take that thing common, you have to do the necessary index manipulation here. So I've taken this part common. So here appropriately the indices have changed. Okay. And the next thing is to combine this term with this term. The third and fourth terms. Is this clear? This one is clear. Please do it. All of you, please do it. Please do the manipulation and see what you get. You don't need to do anything with this term, I guess, because this term was already in that form. You see, it was already in that form. You just need to manipulate this term by adjusting the dummy indices. Then you will get the first 2 terms. So please do it. And for the last 2 terms, if you once again, I want to take, see, what I want to do is I want to take this part common, this U2 U's and 1V. This term I want to take common, and I want to take it common in such a way that I can combine it with this also. Okay. So, 2 U and V. Here also you have 2 U's, 1 V. Here also you have 2 U's, 1 V. So now you do it in step by step way. You just combine the first 2 terms, combine the last 2 terms. And after doing this combination, the final combination is combine everything. So if you do that manipulation, what you will land up to is the following. You have gamma A E gamma C minus gamma A E gamma C B. I'll check it. You have a minus sign. Because what I'm writing is completely correct. I have not made any error in my calculation. You have to just verify yourself. Gamma A ED. So you have a minus in front, then bracket gamma A ED multiplied by gamma EBC minus gamma A BD gamma ECD bracket closed multiplied by UB QCBD. So you see that this combination is already there. Please check it whether you get it in this form or not. Please check. It check করো এটা খুব It is not difficult. It is not at all difficult. You just need to combine the last two terms in such a way so that you get this thing as common. And now it is simple. You can combine all things because this is already common. So you can just remove this part. You can just remove this part. So here also we had a minus. Take the minus common. This is just plus minus here. This UV UCB. That's it. Gamma D ABC minus C ABD plus gamma AEB EC minus gamma ABE gamma ECD. बोल तो बोल ले. So this is fine. And this thing, finally, we have already seen what the Riemann curvature tensor is. And if you just put in the definition of the Riemann curvature tensor, the way we have defined it, is nothing but R A E E U B. So let me write down the equation in a nice form. So our aim was to calculate this quantity. This quantity, nothing but this B, where RABCD is nothing but the quantity inside the bracket. And you just check whether the definition that I gave you earlier for the Riemann curvature tensor agrees with this or not. Please check it. You will see that this is precisely the Riemann curvature tensor. And this equation that we get for the deviation vector is the second order derivative with respect to tau. This is called the geodesic deviation equation. It's a very important equation. The geodesic deviation equation. It tells you that the second derivative of this VA is proportional to the Riemann curvature tensor. So the separation between the geodesics as the parameter tau is changing, this separation, so this is basically the separation vector of the deviation vector. And this measures the evolution of this separation vector or the deviation vector as you move along the geodesic, right? As tau changes. So it tells you that this separation VA will not change. It will remain the same if the curvature vanishes. If the right hand side is 0, then this separation will not change. So it will remain as it is. But it tells you that this curvature basically tells you that it is a measure whether the geodesics are coming close or they are moving away from each other. That is what it gives you. So in the presence of a gravitational field, please write this down. In the presence of a gravitational field, a group of geodesics, in the presence of a gravitational field, a group of geodesics do not remain parallel. So in the presence of a gravitational field means if you have a gravitational field, then this curvature tensor, Riemann curvature tensor will be non-zero, right? And then what will happen is the following. A group of geodesics will not remain parallel. This is known as geodesic deviation. The fact that they are not parallel, this is known as geodesic deviation. By studying the deviation of geodesics, by studying the deviation of geodesics, we can detect the presence of a gravitational field. By studying the deviation of geodesics, we can detect the presence of a gravitational field. Is this clear? So, what are the things that we have learned so far? We have, if you summarize from the beginning, we have learned about the various derivatives. One is a covariant derivative, one is a B derivative. Parallel transport. From parallel transport, we have seen what the geodesic equation is. It gives you the trajectory of a free particle in a gravitational field. That is the geodesic equation. And then we have studied the Newtonian limit, right? From geodesic equation, we have seen what the Newtonian limit is. And today, what we have learned is another important equation, which is the geodesic deviation equation. So these are the things that we have learned so far. So if you have any questions at this point, I think it is a good place to stop here today. I will carry on from here on Wednesday. So if you have any questions at this point, please ask.
Sir. Yes, sir.
Okay.
First question is from the geodesic equation,
Mhm.
we started it from for the free particle.